Ready?
Yes, sir.
Good morning to my dear students. Okay, this was the last slide for yesterday's batch. Okay, the recorded video is being uploaded in YouTube. Okay, so I advise you to go through. Then only you can follow the further. Today is seismology. It is going to be over. Okay, I will finish up this one. What is the next slide? Right. See, actually, I told you in India, January 26th, 2001. In Gujarat, there was an earthquake in the city Ahmedabad, huge danger. Okay, the damage was very severe. Right? All of you see here, if you happen to see the scene of those cities, you never prefer to live in apartments. If you happen to see the scene of those cities, that time, you never prefer to live in apartments. You fear to live in apartments. Okay? So see, most of the building damages, don't think only old buildings are damaged. Masonry buildings are damaged, Paka RCC house withstood. No. Even the newly constructed RCC building, even RCC building which were under construction, newly constructed one, also undergone severe damage. The reason was poor construction practice. Okay, some negligence, unaware of detailing fault. Okay, detailing fault. Let us see this one. See, some few pictures I have shown. The demolition. Okay. The demolished structure of it. You see, apartment, especially the staircases. Staircases failure in apartments of our huge in our own country, India. Not like some part of the world, no. It is here only in India only. Okay. See here, these are the damages. Let's go group it. Later one by one we will discuss. Okay. See here, beam column joint. Most of the beam column joint have found failed. Observed, okay, observed, found failed, beam column joint. What is the reason behind it? I will tell you, I will explain. By going through the image one by one, I will explain. Okay, so this is the Andaman Nicobar. What were damage during Sumatra earthquake? Okay, you can have a look at that also. Seismic zones in India. First I want to tell you that, later I will go to the lessons learned from past earthquake. Okay, seismic zones in India. Seismic zone. IS 1893, the seismic zone map of India is given, which was in 1984, again revised during 2002, after Gujarat earthquake. After Gujarat earthquake, earlier, 1984, seismic zone of India, thereby India have been divided into 5 zones. When during 1984, the board prevailed up to 2001, up to Gujarat earthquake, up to that. Okay. There were 5 zones, zone 1, zone 2, zone 3, zone 4, zone 5. Okay, so are shown here. The zone, the white color, zone 1s are earthquake-free area, regions, earthquake-free region. They are not earthquake-prone. While other colors are earthquake-prone. Okay, severity is shown. Now, after the Sumatra earthquake, it has been realized the entire region of India is earthquake-prone. There is no earthquake-free area, there is no earthquake-free region in India. The entire, all regions of India is earthquake-prone. So that is the decision made by the experts, okay, seismologists. So that is why what they have done, they merged zone 1 with zone 2. No white color, only you can see the blue color. Zone 1 is merged with zone 2. Now the India have been divided into only 4 seismic zones. Zone 2, Zone 3, Zone 4, Zone 5. Okay, 4 seismic zones. Zone 5 means severe, highly prone. Okay, highly earthquake-prone. That is the meaning of it. I will show you the individual zone map of India. This is the 1984 one. You can see India was up last time. Was divided into 4 seismic zones from 1984 to up to 2001. It was 5 seismic zones. The white was earthquake-free zone. Okay. But later, after the earthquake 2001, in the 2002, it has been revised into like you see, 4 seismic zones, zone 2, zone 3, zone 4, zone 5. You can have zone blue color or zone 1. Okay, many regions of India have been upgraded into higher seismic zone. Listen here, many regions of India have been upgraded into higher seismic zone. For example, Chennai, which was originally in zone 2 earlier, have been upgraded to zone 3. Okay, Pondicherry is still in zone 2 only. But experts are telling, keeping in view the intensity of population and intensity of infrastructure, okay, it is advisable to design structure in Pondicherry as for zone 3. Although the zone map Pondicherry is in zone 2, it is advisable to consider it as zone 3, keeping in view the intensity of population and the intensity of infrastructure of Pondicherry city. Likewise, okay. And since many region in India have been upgraded to higher seismic zone, what is the other problem people faced? Experts, not problem, they got a problem to solve. That was, listen, don't talk, listen, what they decided, structure, which many structures have not been done exploration. Okay, the zone was not considered exploration, design has not been done. Certain structures have been, have been designed for exploit, okay, for zone 2, which were lower zone. They were originally designed for lower zone. Now they are declaring that the region belongs to higher zone. Okay, they are upgrading that region to higher zone. Now we have to revisit the safety of that structure. Okay, we have to revisit the safety of those structures. Okay, now the other problem was evaluation of existing building. Seismic evaluation of existing building. It's whether it's vulnerable or not. In other words, seismic qualification of existing building, whether it's qualified or not. The building will be safe or not for the upgraded zone. Okay, because it was originally designed for lower zone and constructed, it is existing. Okay, now we are declaring it, the region is identified as higher zone, but it was originally designed for lower zone, zone 2. Now it is at zone 3. Now zone 3, if you have to lateral force and revisit, reanalyze. Again you have to analyze the building and see whether the reinforcement provided in the building will safeguard, is it safe or not, or is there any efficient member in the structure. That is called evaluation. Evaluation of seismic evaluation of existing structure, and then suggesting certain retrofitting strategy to prevent, okay, to prevent vulnerability, to reduce the vulnerability of the building. That was the problem we have taken in hand at that time. That was popular. Many of my M.Tech administration work I guided on that day. We taken some existing building in Pondicherry, which were originally designed for zone 2. Now we assumed the Pondicherry to be upgraded into zone 3. Then we evaluated the existing buildings, certain hospital, VIII hospital, some Tanandri block, and some other block we have taken in Puducherry. And even education department building we have taken once, okay, for certain branch. Even Women Children's Hospital one student have taken, and we reanalyzed it for higher zone, okay. And we analyzed, and thus we come to know is there any deficient structure, whether the reinforcement provided are sufficient or not. Is there any deficient member? If any deficient member is found, how to retrofitting it. So what retrofitting strategies shall we adopt? And we suggested certain strategies for retrofitting. Likewise, the report was done. Not only we followed what many IIT Chennai, National Laboratory like the Structural Research Center, they were taking project and they were working on that. For that, how do we do that? Some guidelines required to do certain calculation, computation, to evaluate. To evaluate the existing structure, what is the guidelines required to be adopted? Certain guidelines were framed by international level by a body called FEMA, FEMA. Okay, the management agency was the FEMA, Federal Emergency Management Agency. Federal Emergency Management Agency, FEMA. And then another body, okay, they are non-government body of United States, called ATC, Applied Technological Council, under FEMA, that was under B.Tech. ATC, Applied Technological Council. That ATC under FEMA released guidelines for evaluating the existing building and suggesting the retrofitting strategy. That was the project we have taken, even for B.Tech. For M.Tech, several projects were getting on that area for several years. Okay, since 2001 to 2002 up to 2006-07 we were getting projects on that area. That you remember, right? So This is the extra additional slide. So let's see what is there. See what is the level of shaking magnitude. Magnitude will be high. It means more energy distance, magnitude will be more. And distance, shaking becomes distance. Okay, episodic distance. Local soil. Sometimes the local soil amplifies the shaking. Some additional energy. Okay. Let's see the effect of earthquake damage to infrastructure. I already told you. This photo shows the effects of earthquake. Okay, just some going to end there. Some additional photos are there. This one shows the damage, the ground shaking and its effect. Okay, not the see okay, see the damage households, landings, and infrastructure failure like grid failure during power grid earthquake. Okay, this photo was taken from the US Geological Survey. Okay, they released it from grid and then ground shaking affects damage to the buildings, COVID, Japan earthquake. Okay, this is very good. Japan earthquake 1995. This is very interesting one. See, we have learned a lot of lessons from past experience. This damage to the building taught us some lessons. I will come to that later. From this, what the experts have learned, see here, this building is intact, no damage. So we go through the head, no much damage. Only a particular floor got crushed. That's the after change, there's a projection. That's the projection, top projection is there in the building. That particular floor crushed. The reason is, so the experts have realized there should not be any abrupt change in the stiffness of the building in the vertical direction. There should not be any irregularities in the vertical direction, called irregularities. All these things have been discussed in your ISO 1893. Vertical and horizontal irregularities are discussed in that. Okay, so the building should be as much as possible. In other words, I can say this way: the load path should be continuous. The column which carries the load from the floor, it comes away against them, which is the projection. The projection. You take the projection, the place of the building, the top. The column which carries the load comes away against them, which are called floating columns. So floating columns are to be avoided. Otherwise, the load path should be continuous. There should not be any discontinuity in the load path. I can put that way. Otherwise, there should not be any abrupt change in the total stiffness of the building. Because you take bottom portion, there are so many columns inside the building. You take the sum of the lateral stiffness of each column. What is lateral stiffness? Force equal to cos unit deformation. Okay, what is this stiffness? You take a cantilever, take each column. Imagine a bottom fixed. Top, at the top, what is the force equal to cos unit deformation? That is called stiffness. Okay, you add the stiffness of each column. Okay, so here columns are less, there more. Suddenly, abrupt change in the stiffness is there. If you add the stiffness of all the columns, it is higher. If the difference is more than 80, if the difference is more than 20%, okay, then okay. If the stiffness of this floor is less than 80% of the upper one, that is called soft story. So normally wherever there is a abrupt change in stiffness, the force focus, concentrate there. The lateral force focus there, concentrate there, and cause failure. That is why it is building that particular floor alone got crushed. Okay, people were all other things are intact. Only that floor gone. Might be shear failure. Okay, just focus. Lateral forces concentrate. Shear failure. Might be cause shear failure there. Due to abrupt change in stiffness in the vertical direction. Irregularity in the vertical direction. That should not be mass irregularity or stiffness irregularity in any direction, vertical or horizontal direction. Wherever abrupt change in mass, abrupt change in stiffness comes, the building, the lateral force concentrate on the section where abrupt change is there and fails. Okay, that's what I learned from this photo. Right? And then surface walling is okay. This is a beautiful, most popular picture for which shows the effect of liquefaction. The phenomenon of liquefaction already I have told you. I showed a lot of video animations. Okay, whether you for your batch or other batch, I don't know. But I hope you might have seen the videos. All the videos you might have seen. That I will explain. Okay, the phenomenon of liquefaction, sand boiling. Phenomenon of liquefaction already I explained. So see the buildings printed. It is in Nagata, Japan, 1964. See the apartments are intact, no damage, no structural damage to them. But they are tilted due to geotechnical failure, soil failure, by the phenomenon of liquefaction. I already explained what is liquefaction, very nicely animation and all. I advise you to go through the video later or revise it. Okay. So see the many models are tilted due to the phenomenon of liquefaction, geotechnical failure of the building. Okay. So here I am just telling the effects. And also landslides. That also one of the effects I told you. Right? Fire. Living earthquake, fire also encountered. Okay, overhead earthquake. Tsunami. Okay. So these are tsunami. See, if tsunami fault subduction zone, just this picture, this is maybe is going to be over. Something to know. I told you how the bedrock rebound. Okay, and pushes the water mass. When the deep sea. It is 5 kilometers. The depth of sea is more than 5 kilometers. The tsunami travels with 830 kilometers per hour, more than the flight speed. More than flight speed it travels. When it is reaching near the shore, its velocity reduces to 350 kilometers per hour. And then when it comes to near zone, 50 kilometers per hour. When the bed depth reduces, the tsunami, the wave height will keep on increasing. But there is a limitation. Okay, the wave height cannot increase further. Okay, it's a kinetic energy. The wave brings kinetic energy. And then, since there is a limiting value for the wave height, it breaks and dissipates energy into heat energy. The wave breaks and dissipates energy into heat. Just it comes with kinetic energy. The earthquake energy pushes the water mass. The water mass travels with kinetic energy. And nearing the shore, the wave height keep on increasing. When certain limiting value are attained, the wave breaks. Thus dissipate energy and convert the energy into heat. Because the energy can be created or can be destroyed. It is converted into another form. Okay, that's what we keep it in mind. So with this slide is over. Okay, this slide is very good. This slide is over with this. Right? Very good. So almost I have completed first unit. First unit is over for you. Now you take down unit 2. Write down unit 2. Now I am going to unit 2. Also write down unit 2. Right? Unit 2 is here in this folder. I will go to the old presentation that is here. Right. So here, write down unit 2. Under unit 2, first what I am going to discuss, lessons learned from past histories. Give heading. Lessons learned from past histories. Okay. Lessons learned from past histories. We see here, we have, as far as restitution is concerned, the experts have learned a lot of lessons from past histories. Don't take it lightly. Past history means we have learned a lot of lessons from others' pain. People have died, many people have died in painful way. They were buried alive, they were crushed to death. From their pain, we have learned a lot of lessons. Okay, from others' pain, we have learned lessons, I would say. To be more, okay, in other words. Right? So, lessons learned from past histories. Just I will tell you. I have a collection of VIII disaster. VIII, no? So, one team from IIT Kanpur and ISC Bangalore. Process of IIT Kanpur and ISC Bangalore. Immediately, the VIII earthquake, Gujarat earthquake, they visited and took photo, the team. That collection, I got it from, I am not sure whether the ISC Bangalore website or from IIT Kanpur website, I don't remember exactly, but I have the collection of images. Okay, so the folder name is Disaster VIII Images. Okay, just I will open it and I will have learned some lessons. In that it is categorized. Okay, here bridges, earthen dams, failure of bridges, failure of earthen dams, charging of failure, emergency response and relief. Okay, good performance, installing models, industry failure, lifeline utilities are failure, and ports, failure of ports, railway failure, structures, typical major things. Okay, structures. I will go to that folder. All these are lessons for you. I will go to that structures. Okay, may not necessary. In that structures, I have two folder: masonry structure and then RCC structure. We will go to RCC structure. Normally, what you will think, doing earthquake, masonry structures are unvulnerable. They may be damaged easily. But RCC structures are safe. But that they will not be damaged much. But have a look at it. The RCC. I am going to show you what happened to the RCC, which we are thinking strong. Okay. Right. See here, before the team reached, the building owner strengthened it. column is there. The building owner strengthened that column. Okay, strengthened it. Do you know the difference between strengthening, repairing, strengthening, rehabilitation, retrofitting? There are different terms. But I did not understand it. I don't want to give you the explanation. But still listen. Okay. So this one, this way they put additional columns, 3 columns, and then with the ladders like this. Let us see. Only few pictures we will discuss. Right? Oh my God. Okay. See here the column have failed. Okay, the column have failed. Actually, if you look at the failure, okay, if you look at the failure, it is called a short column failure. This one, it is observed that short column fails. How means, see here, there is a jolly one opening almost. In between there is a brick infill. At the brick infill there is no damage. Here this opening side, if it is a full height, no problem. Only here at the top of that one, the jolly area, the column has failed, hinge formed, maybe shear failure. And also that column, that portion, failures, that is called short column effect. Short column effect. Short columns are vulnerable for shear failure. Okay, force will, lateral force will focus there, concentrate there, because abrupt change in stiffness. Why? There is a infill available, no? There that portion of the column stiffness is very good. Wherever there is an opening or some jolly work is there, the portion of the column stiffness reduces. That is why the junction where abrupt change in stiffness is there, the lateral force focus and cause some maybe natural failure or shear failure. There might be shear hinge. Okay, cause it. Right, hanging actually. Right. See here, hinge formation in a column. Hinge form. Please allow to see here, when the building frame is subject to lateral loads, if you see the bending moment diagram to draw, the bending moment are very like this, like triangle, like this, bending moment diagram. Bending moment diagram will be like this, and linear, okay, lateral goes there. Is it necessary to draw on the board? Hope you will understand what I am trying to tell, okay. So, the bending moment value is 0 at mid-height of the column, because the bending moment changes sign when the building frame is subject to lateral loads. Okay, top of the column, bending moment is high. At bottom of the column, bending moment is high. When it vibrates, it changes its phases. Okay, this bending moment diagram comes like this. Okay, bending moment diagram. Okay, because when the building vibrates, always at the center of the middle height of the column, bending moment value is 0. At top and bottom, that change in that stress, I would say bending moment diagram, change the phase load is in that side, due to which it is a plastic hinge zone. That those portions are called critical zones, which are there plastic hinge will form. They are potential plastic hinge zones where hinge will form. Hinge means that is called hinge. Hinge will form, right? So normally in practice, what is the practice being followed? I have constructed first floor. How do I construct the second floor of this building? While constructing first floor, some steel bar will be protruding here. Yeah, protruding here. And I will cast this slab. Afterwards, the overlapping will be done here. I will take another piece of steel and do the overlapping either by coupling or by tying, overlapping and tying, or welding, overlapping and welding, and bar will be there. Then I will construct this column. That is a wrong practice. Overlap places are to be avoided here, where plastic hinge zone likely to form. Okay, where plastic hinge zone there and here, that's wrong practice. Actually, overlap places are to be provided from the mid-height of the column. While casting this first floor slab, this bar should be protruded up to this one. It should be extended up to mid height. Okay. From there you have to do either jacking, there is a coupling, or you are welding. Okay, and it should be taken. This is strictly followed in the Fortis building. I have observed when the Fortis building construction was going on. I was standing in the Saint Teresa Street and observing. So they were strictly adopted. Okay, the moral of spices they provided at mid height of the column, each column. Okay, keep it in mind. Sometimes some experts will ask questions like this. Why do you provide moral of spices at the mid height of the column? Write down. Why do you provide moral of spices only at the mid height of the column? Or in other words, why do moral of spices to be provided at the mid height of the column? Why do moral of spices are to be provided at the mid height of the column? If it is the question you get, immediately you have to draw the what you have to draw. You have to draw the bending moment diagram. Okay. When you are subject to that on the course. Okay. I have told you how we can start this from there. So okay, no problem. Okay. So I told you the column bending moment diagram. You take a column. Okay. Bending diagram will be like this. So it's subject to random rows. Okay, this is the column. The bending diagram will be like this. Okay. When it changes its face, when it's vibrating, then it becomes like this. Bending diagram. Here the bending mode changes line. Value is 0. Here bending mode values are high. So they are called potential plastic inflows. That you have to avoid. Okay, the potential plastic inflows, you have to avoid overlap prices. Okay, so this is the lesson learned. Okay, from the failure. Yeah, see, hinge formation. Actually, the hinge is formed due to inadequate confinement. The ladder is provided here. Okay, it's not provided properly. They have normally in practice they are kept 1 feet apart. Many mason do like that. Many barbender do like that. They simply keep the laterals 1 meter apart. If you ask them why are you providing lateral springs? Why are you providing rings? Their level of understanding is they will tell to keep the longitudinal bar in position. To hold the longitudinal bar in position, I am providing these rings. That is their level of understanding. In beams, I am providing straps. In column, I am providing lateral ties. In order to keep the longitudinal bars of the member in position. That is mason or barbender level of understanding. You are engineers, you should know. In beam, we provide that one straps to resist shear. Actually, in column also, we provide laterals to resist shear. It will, that the lateral provider should also take a confinement action. You should provide confinement. If the laterals are placed at the closest spacing, this core concrete would not have got crushed. Here see the core concrete crushed. Core concrete means outside the reinforcement gauge you have cover concrete. Spalling is there. Inside the reinforcement gauge you have concrete, called core concrete. The core concrete crushed. Okay, because of inadequate confinement. Moreover, the confinement have opened, ties have opened easily because they are bent only 90 degrees. So what expert says, it should be bent 135 degrees. It should be embedded inside, anchored inside. The ring is there, no? Just we are bending it 90 degrees. It should be bent like this. It should go inside the concrete to record anchor length. 10 times, at least 10 times the diameter of the bar. 10 times the diameter of the bar, it should be, suppose you are using 8 mm dia straps. 8 mm it should be embedded inside. Called 135 degree hook. 135 degree hook to be provided. In that case, it will not open easily, and also it will provide the required confinement action. Moreover, they have to be placed at minimum spacing, where potential critical zones, potential heat zones. Okay, what is the practically as far as called minimum spacing? It should not less than 75 mm. At least 80 mm. Okay, 80 mm apart should be provided. 8 cm apart, 4 inch apart, at least 3 inch or 4 inch apart should be provided. But what in practice they do 12 inch ones. Okay, 1 feet ones. The people do. Barbender do it. Okay, that is barbender does it. No, that is wrong. Right. That's what potential classing influence learned. Okay, so most of the columns are the potential classing influence failed. Right? Here also some top of the column cracks observed. There are also some swelling is there. Top of the column. This column also due to formation beam column joint. especially at columns which are formed, which is permitted to form in beams. We have a strong column and weak beam concept. The failure mode should be weak beam, strong column. Okay, which may form in column. Sorry, in beams at the end of the beam. Plastic beam should form, but in column it should be avoided as much as possible. Okay, it may be structural sharing it. If you are interested in research level, you will not think too much about it, right? What is maybe structural or what is sharing, you will not think too much. It is a research level thinking. So that's what short column effect I told you. Short column effect. See here, addition to that there is another column. In that column no damage. In that column no damage. Here there is a column with some wall infill. That short portion of the column is sustained damage comparatively. Comparatively undergone damage. Okay. So that shows that is called short column effect. This is subject to failure in shear. And also this one is the top of those columns. Okay, you can see. These are the see projection, water type. In this figure, see all new apartment building, Pakka buildings, see that. Gujarat Bhuj, see that. Pakka buildings. Having a nice new university road, the water type. So projections are to be avoided as much as possible. Have a water type as damage. Okay, here also you see open area, parking area is open ground story.